In the early 20th century, a young physicist named Albert Einstein forever changed our understanding of the cosmos. His revolutionary theories of relativity, special and general, unveiled a universe stranger and more wondrous than we could have imagined. These groundbreaking ideas weren't just abstract equations, they were keys to unlocking some of the universe's deepest secrets, forever altering our perception of space, time, and gravity. Before Einstein, physicists viewed space and time as separate and absolute entities. Time, like a river, flowed at a constant rate for everyone, everywhere. Einstein challenged this notion, demonstrating that space and time are not independent but interwoven, forming a flexible fabric called spacetime. This fabric, he argued, wasn't rigid but could be warped and stretched by the presence of mass and energy. Einstein's theories of relativity, like any scientific breakthrough, were not born in a vacuum. They emerged from a rich tapestry of prior scientific thought and observation, building upon the work of giants like Isaac Newton while simultaneously challenging their long-held assumptions. In doing so, Einstein opened up new avenues of inquiry, propelling us into a new era of cosmological exploration. Published in 1915, Einstein's theory of general relativity is his masterpiece, a profound idea that revolutionized our understanding of gravity. It fundamentally changed the way we perceive the universe and our place within it. It proposes that gravity is not a force acting over a distance, as Newton believed, but rather a consequence of the curvature of space-time itself. This curvature is caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball's weight causes the trampoline's surface to sag, creating a dip. This is analogous to how massive objects like stars and planets warp the fabric of space-time around them. The more massive the object, the greater the warp. Now imagine rolling a marble across the trampoline. Instead of traveling in a straight line, the marble's path curves as it follows the contours of the indented surface. This is similar to how the curvature of space-time, caused by massive objects, dictates the path of light and other objects moving through the cosmos. This bending of paths is a direct consequence of the warping of space-time. Gravity, according to Einstein, is not a force pulling objects down but rather the curvature of space-time telling these objects how to move. This concept has been confirmed through numerous experiments and observations. General relativity provides a framework for understanding the large-scale structure and evolution of the universe. It helps explain phenomena ranging from the orbits of planets to the expansion of the universe itself. It predicts the existence of exotic phenomena like black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These regions challenge our understanding of physics and push the boundaries of scientific knowledge. It also explains the observed bending of starlight around massive objects, a phenomenon known as gravitational lensing, providing observational evidence for the warping of space-time. This effect allows astronomers to study distant galaxies and understand the distribution of dark matter in the universe. Published in 1905, a decade before his general theory, Einstein's special relativity was a groundbreaking work that fundamentally changed our understanding of the universe. This theory focuses on the relationship between space and time in the absence of gravity, providing a new framework for understanding how the universe operates at high speeds. Special relativity rests on two fundamental postulates, the first being that the laws of physics are the same for all observers in uniform motion, meaning that no matter how fast you are moving, the basic rules of physics apply equally. The second postulate states that the speed of light in a vacuum is constant for all observers, regardless of their relative motion, which was a revolutionary idea at the time. These seemingly simple postulates lead to mind-bending consequences that challenge our everyday experiences and intuitions. One of the most intriguing implications of special relativity is time dilation, the concept that time is not absolute but is relative to the observer's frame of reference. This means that time can pass at different rates for different observers, depending on their relative motion. Imagine two identical clocks, one stationary and the other moving at a significant fraction of the speed of light. Special relativity predicts that time will pass slower for the moving clock relative to the stationary one, a phenomenon that has been confirmed by numerous experiments. This effect, though negligible at everyday speeds, becomes increasingly pronounced as an object approaches the speed of light, making it a significant factor in high-speed travel. Another bizarre consequence of special relativity is length contraction, which states that the length of an object moving at a significant fraction of the speed of light will appear shorter in the direction of motion from the perspective of a stationary observer. This effect is not just a visual trick but a real, measurable phenomenon. This isn't an optical illusion but a real physical phenomenon arising from the nature of space-time itself, fundamentally altering our understanding of the universe. Section 4. Two sides of the same coin, comparing general and special relativity. While general and special relativity are often presented as distinct theories, they are, in essence, two sides of the same coin. Special relativity, with its focus on uniform motion and the absence of gravity, can be considered a special case of the more comprehensive general relativity, which incorporates gravity as a consequence of space-time curvature. Both theories fundamentally alter our understanding of space and time, demonstrating their interconnected nature. Special relativity deals with inertial frames of reference, where objects in motion are not accelerating. In contrast, general relativity extends this concept to include accelerated frames of reference and gravity, which Einstein brilliantly realized are equivalent. This equivalence principle is often illustrated by imagining an observer in a closed elevator. The observer cannot distinguish between the downward pull of gravity and the upward acceleration of the elevator because both scenarios produce the same physical effects. Despite their interconnectedness, the two theories have different realms of applicability. Special relativity excels in describing the behavior of objects moving at high speeds, particularly those approaching the speed of light. On the other hand, general relativity shines in explaining the behavior of massive objects and the large-scale structure of the universe. Section 5. From GPS to black holes. Practical implications of relativity. Einstein's theories of relativity, often perceived as abstract and esoteric, have surprisingly tangible implications for our everyday lives. These theories, which revolutionized our understanding of space, time, and gravity, are not just confined to the realm of theoretical physics. The Global Positioning System, or GPS, a technology we rely on for navigation, wouldn't function accurately without incorporating the principles of both special and general relativity. This is a prime example of how complex scientific theories directly impact our daily routines. GPS satellites orbit the Earth at high speeds, where time dilation as predicted by special relativity is significant. This means that time actually runs slightly slower for these satellites compared to clocks on the ground. Moreover, the satellites are situated in a weaker gravitational field than clocks on Earth's surface. This difference in gravitational strength causes time to pass more quickly for the satellites, a phenomenon explained by general relativity. This difference in gravitational potential affects the flow of time, as predicted by general relativity. The combined effects of special and general relativity mean that the clocks on GPS satellites and those on Earth do not tick at the same rate. To ensure accurate positioning, GPS systems must account for these relativistic effects, making minuscule adjustments to the timing signals received from the satellites. These adjustments are crucial for the system's precision. Without these corrections, GPS navigation systems would accumulate errors of several miles each day, rendering them practically useless. This highlights the indispensable role of relativity in modern technology. Beyond GPS, the impact of Einstein's theories reverberates throughout modern physics and astronomy. They provide the foundation for much of our current understanding of the universe. General relativity provides the theoretical framework for understanding the evolution of the universe, the behavior of black holes, and the existence of gravitational waves, ripples in space-time caused by the acceleration of massive objects. These concepts have opened new frontiers in scientific research. The recent detection of gravitational waves, a century after their prediction by Einstein, stands as a testament to the power and predictive capability of his theories. This discovery has ushered in a new era of astrophysics, allowing us to observe the universe in ways previously thought impossible. Section 6. Einstein's Legacy, a Foundation for Modern Physics. Einstein's theories of relativity weren't merely incremental advancements in our scientific understanding. They were seismic shifts in our perception of the cosmos. They challenged centuries-old assumptions about the nature of space, time, and gravity, replacing them with a more nuanced and counterintuitive view. This paradigm shift laid the foundation for much of modern physics, including cosmology, astrophysics, and particle physics. His work inspired generations of scientists, to probe the universe's mysteries with renewed vigor and imagination. The quest to unify general relativity with quantum mechanics, the other pillar of modern physics, continues to drive research at the forefront of theoretical physics. This unification, if achieved, promises to unlock even deeper secrets about the universe's inner workings, potentially revealing the quantum nature of gravity itself. Einstein's legacy extends beyond the realm of science. His name has become synonymous with genius, his image an icon of intellectual curiosity, his unwavering pursuit of truth, his willingness to challenge established dogma, and his profound insights into the workings of the universe continue to inspire awe and wonder, reminding us of the power of human ingenuity to decipher the cosmos's grand design.